In this unit, we will be diving into systems of first-order linear ODEs. So sometimes in differential equations, when we have multiple differential equations, we rely on linear algebra to solve systems of differential equations. And in this lecture, we will not be diving too deep into the linear algebra world. However, we will be reviewing and understanding what a system of first order linear differential equation is and some basic methods to solve it, and basically just introducing this new concept. So usually we will have in a first order linear ODE, we will have an x prime term. This is a function of t, and will be equal to a function of x and y. Likewise, we will be having the same thing for y, and this is also going to be a function of t. And sometimes we will have decoupled and coupled differential equation systems. And basically, when we have a decoupled system, this function on the top will only be termed in terms of x because x is the variable, and this one will only be in terms of y. However, if it's coupled, it means that the function will be both in terms of x and y. So in coupled different systems, we will be using both equations to solve an equation. However, if it's a decoupled system, we will solve these systems separately, and these systems will generate different answers depending on these functions. Now I'd like to give you an example on decoupled systems. Here, as you can see, x prime equals to 2x and y prime equals to negative y. So we don't have any x terms in the second function, and we don't have any y terms in the first function. So basically, these are decoupled because you don't have them in their own equations. You don't have any y terms in the x prime equation, and you don't have any x terms in the y prime equation. So this is a decoupled system. And we will treat these equations as separate equations, and we'll try to solve these on our own. So x prime will be equal to 2x. So this is basic first order differential equation. What we can do is separable would definitely solve this differential equation. Dx over dt, guys, because remember this is a function of t, so dx over dt equals to 2x. Therefore, this implies dx over 2x equals to 2 dt. And we can go ahead and integrate, and this will mean that 1 over 2 integral 1 over x dx equals to t plus c, and this integral will be 1 over 2 ln of x equals to t plus c. Multiplying everything with 2, we will have equation ln x equals to 2t plus c. Take the e term, and we will have x equals to e to the 2t, and multiplied with c because e to the c is also another constant. As you can see, when I multiplied with 2, I didn't multiply c with 2. It's because c is a constant. So the solution for the first one will be x equals to e to the 2t power, okay, times constant. So this is how you should solve the coupled systems. Now, I'd like to move on to the second system. So basically, y prime, okay, y prime equals to negative y, so dy over dx, dt, my bad, will be equal to negative y. Also, we could use integrating factor method to solve these two because these are first order linear ordinary differential equations. Um, However, I just wanted to do separable. So this will imply negative 1 over y dy equals to dt. Integrating both sides will give us negative ln of y equals to t plus c, and we will have ln of y equals to negative t plus c, and y would be equal to e to the negative t multiplied with c, just like this here. Um, exactly. So this is the solution for the second equation. And if you combine these solutions together, you will basically have the solution for these each differential equation. You will have a solution. Now let's work on this coupled system. As you can see, this y term is in the first differential equation, and this y is obviously dependent on the second equation. So the way we can solve these equations is try to find one of the variables, and once you solve for either x or y, you are basically able to solve the entire system. So the first thing I want to do is start with y prime equals to 0 because it's really simple. How can a derivative be equal to 0? I'd like to ask you this question. How can a derivative be equal to 0? Basically, if you integrate a constant, right? A constant number, the derivative of a constant number is 0, okay? So dt of a constant equals to 0. So basically, this implies that y equals to a constant, okay? Now that we know that y equals to a constant, we can go ahead and plug that into our first differential equation. X plus c is equal to x prime. And now we can use dx over dt, the separable method, to solve this differential equation. So we will have dt equals to 1 over x plus c dx. All right. And now this will give you ln of x plus c and equal to dt plus c. Well, yeah, we could call this a c2. It doesn't really matter. And x plus c will be equal to e to the t multiplied with a constant. And the x will ultimately be equal to e to the t times a constant minus constant 2. You could call a constant 2. It wouldn't really matter, but at this point, this constant can actually account for this other constant. So yeah, you don't actually need to put this subtraction here because we could have any constant and we could basically generate we could actually account for that subtraction as well. So this would eventually be our solution for this coupled system. And just to make a brief recap, we just solved for y, and y was this constant, and using this fact that y was a constant, we were able to solve the first and most complicated equation in this system. Now let's make a brief observation on the matrix form. So I know many of you probably didn't take linear algebra. For you who took linear algebra, this is fairly simple. When we have a different system of differential equations, we like to put these in matrix forms because matrix forms are so useful and we can do so many operations on them that we could solve simultaneous many systems of equations, many equations together in a very, very easy way. And linear algebra helps us a lot. So on the left, we would have a x prime and a y prime as two different functions of t, and they are equal to, we have one matrix a, b, c, d, all of them are constants multiplied with variables x and y. Well, I want to show you how matrix multiplication is done. So when you have any, you want to count the rows in the columns first. So over here in this matrix, the first matrix, a matrix is when we have these brackets, by the way. We want to count how many rows and columns it has. So this matrix has 1 and 2 columns and one and 2 rows and 1 and 2 columns. So this is why it's going to be a 2 by 2 matrix. Over here we have 2 rows in this matrix. There's 2 rows and 1 column. Okay, so this will be a 2 by 1 matrix. This represents a row multiplied with the column. Okay, so we have a 2 by 2 and a 2 by 1, and in order to make a multiplication with matrices, you want to have the same constant on the right hand side of the first matrix and the left hand side with the second matrix. So if I had a 3 by 3 matrix multiplied with a 3 by 1 matrix, that would work, but a 3 by 3 matrix multiplied with a 1 by 3 matrix would not work because this 1 is not equal to this 3. So this is important theory on how we could multiply on matrices. And when you want to multiply, you just grab the column and multiply with the first row and keep doing that, okay? So the column times the row, and we will have, and more importantly, our new matrix will be 2 by 1, okay? This is also by theory. The left-hand side of the first matrix and the right-hand side of the second matrix will be our indexes for the resultant matrix 2 by 1. So we know that this will generate a 2 by 1 matrix. The first term will be this guys multiplied with these guys and basically adding them each other. So we will multiply a and x. Okay, so I'm going to take this and multiply with this. So ax plus by. Okay, I'm going to multiply this with this and this with this. So just grab this. Imagine you grab this and put this in like a vertical way and multiply these one by one, and this will be your first index, the first entry of the matrix, a vector matrix. A vector matrix is when we have one column, by the way. And for the second one, we would take this guy and multiply this guy, so we would have cx plus dy. And this is basically the same as this multiplication, guys. Okay? And another important note, when we're using these linear algebraic matrices in our equations, we usually, not usually, all the time, we mean that this first row is an equation and all of these columns are rows. So the rows are equations and the columns are variables. So I mean, just keep that in your mind, and we will be focusing on that in the future, more detailed. So right now, I just want you to understand matrix multiplication and how you can how you can master that concept. So over here, we like to call this ABCD matrix the constant A matrix, and we will have this xy will be represented as capital X, our variables, and capital X prime will be also our x prime and y prime, and we usually like to express these differential equations just like this: x prime equals to ax. Okay, and these usually help us in the future solve these differential equations when we learn about eigenvalues, eigenvectors, and solution sets for these matrices. We're just going to do pretty much the same things we did before, but we're going to be able to solve systems of differential equations, not a single one, but multiple ones. Sometimes they're dependent on each other, depending on what we have. So these matrix forms will be really crucial for us to understand what's going on here. I'd like to end this video with one example. This is a decoupled system of equations, and let's solve this decoupled system. So first of all, we know that x prime equals to minus 3x, so I'm going to write that in Leibniz notation, dx over dt equals to negative 3x. This implies that negative 1 over 3 times 1 over x dx equals to dt. So we will know that the integral, we're going to take the integral on both sides. Negative 1 over 3 ln of x will be equal to t plus c. And let's multiply everything with negative 3. So ln of x will be equal to negative 3t plus c. As you can see, I'm not multiplying with negative 3 because it's a constant. And basically, our solution for x of t will be e to the negative 3t multiplied with c. Okay, so this is the first solution, and the second solution will be pretty much, we're going to use the same method, dy over dt equals to 4y, and we will know that 1 over 4 times 1 over y dy equals to dt, and 1 over 4 ln of y equals to t plus c. Therefore, ln of y would be equal to 4t plus c. I'm just skipping the algebra. Let me know if you have any questions on the comments. I'm just multiplying this with 4, and we will take the e, so we will have y equals to e to the 4t multiplied with c as our solution for the second equation. So these will provide the solutions for this decoupled system.